The universe is not static. It never has been. But for most of human history, that's exactly what we believed. Look up at the night sky. The stars don't seem to move. The constellations stay the same, night after night, year after year. The moon glides smoothly. The planets wander a little, but always return. To ancient eyes, it all felt permanent, still, like a great cosmic painting hung above the world. So we built our understanding of the universe on that stillness. The Earth, we thought, must be the center, solid and unmoving. Everything else, the sun, the stars, the heavens, must be spinning around us. A perfect celestial dance, set in motion by something divine, but always repeating. For centuries, this view held, not because people lacked imagination, but because it worked. It matched what the eyes could see. It made sense of the seasons. It explained eclipses and alignments. It gave us comfort, a stable world beneath our feet, surrounded by orderly skies. Then came a crack in that illusion. First, Copernicus dared to suggest the Earth might not be the center after all. Then Galileo pointed a telescope at the heavens and saw moons circling Jupiter, proof that not everything orbited us. And then came Kepler, who studied the paths of planets and discovered they didn't move in perfect circles, but in ellipses, guided by invisible forces, following precise mathematical laws. Bit by bit, the stillness faded. Today, we know the truth is far stranger than anyone imagined. Space isn't silent and fixed. It's in motion everywhere. Not just planets and stars, but galaxies, clusters and superclusters. Even the very fabric of space is on the move, stretching in all directions. And yet, we still feel like we're standing still. The ground doesn't shake. The stars don't blur past us. The universe feels calm. But that calm is just a trick of scale, a mirage. Because the truth is, even now, right this second, we're spinning on a planet, orbiting a star, flying through a galaxy, all while being pulled by a force we can't even see. The old picture of a still universe is gone. We've stepped into a story of hidden motion, and we're finally beginning to understand what that motion means. For millennia, the dominant view of the universe had placed Earth at its absolute center. After all, that was what people knew. During the day, they saw clouds glide above them and the sun shine brightly overhead. At night, they saw the moon and the stars stretched out like a giant cosmic painting. Every celestial object appeared to be in motion, and they believed they were at the center of it all. This view was found across the ancient world, from Chinese sky lore to Mayan cosmology. But it was in the Hellenic world that this idea not only became an accepted myth, it was structured into a technical cosmological model. And the man who did that was Claudius Ptolemy. Ptolemy lived in Alexandria around the 2nd century CE, during the height of Roman Egypt. He was a scholar, a mathematician, and more than anything, an astronomer who wanted to make sense of the skies not just philosophically, but with numbers. He inherited a rich tradition, from Babylonian star catalogues Egyptian astronomy, and Greek geometric modeling. But what he did with that knowledge was something monumental. He compiled, organized, and refined it into a systematic model of the cosmos, laid out in a massive work known as the Almagest. The work so influential that it became the definitive guide to the universe for over 1,000 years. In Ptolemy's model, Earth sat at the very center of the universe, perfectly still, unmoving. Around it, in concentric spheres, revolved everything else: the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally, the sphere of fixed stars. Beyond that, nothing humans could know. The entire cosmos was a giant set of nested spheres, perfectly ordered, with Earth as the pivot of all celestial motion. Each celestial body was embedded in a transparent, crystalline sphere that spun smoothly around us. The stars were affixed to the outermost shell, which rotated once every day, giving us night and day. This wasn't just a random guess. Ptolemy used observations to make his model mathematically functional. He believed the heavens must move in perfect circles, because the circle was the most perfect shape in Greek philosophy. But that created a problem. When people tracked the planets over time, especially Mars, Jupiter, and Saturn, they noticed strange behavior. Sometimes a planet would slow down, stop, and even move backward in the sky before resuming its forward path. This retrograde motion made no sense if all the planets moved in simple circles around Earth. To fix that, Ptolemy introduced epicycles. These were small circular paths that each planet traveled, while that entire smaller circle orbited Earth along a larger circle called the deferent. So a planet didn't just circle Earth, it circled a point that itself was circling Earth. This looping motion could recreate the backward steps seen in the sky. But even that wasn't enough. The math didn't quite line up with what astronomers observed. So Ptolemy introduced another tweak: the equant. This was an imaginary point slightly off-center from Earth. He claimed that if you measured the planet's motion from this equant point, the movement appeared uniform, not from the actual center, but from this offset position. The model had been refined for centuries, polished and preserved. It had shaped calendars, timekeeping, astrology, and religious worldviews. It had served empires and guided scholars. It had explained the skies for over 1,000 years. But no amount of complexity could hide the truth forever. Observers were beginning to ask hard questions. A few began looking for a simpler explanation. And one name stood out, a name whose revolution still echoes to this day. It all began quietly, in 1543, with the publication of a book that would shake the foundations of astronomy. Its title was De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. And its author wasn't some famous scientist or thinkers. He was a priest. His name was Nicholas Copernicus. That might sound odd today, but back then, it made sense. The Church was the epicenter of intellectual life in Europe. If you wanted to study mathematics, astronomy, or philosophy, the Church was where you did it. Monasteries and cathedral schools were the libraries and laboratories of their time. Born in what is now Poland, Copernicus studied law and medicine, dabbled in economics, and became fluent in Greek and Latin. But his real passion was the sky. And for years, he had been quietly collecting observations, running calculations, and writing out an idea that had been forming in his mind. One that went against everything he had been taught. His idea challenged the entire system people believed in, so he kept it mostly to himself. For decades he hesitated, knowing the risks, not just scientific criticism, but religious and political backlash too. Near the end of his life, he finally published that idea, reluctantly. In it, he outlined a model of the universe where the sun, not the Earth, was at the center. The Earth, he said, was a planet, just like Mars and Jupiter, and it orbited the sun once a year. But he didn't stop there. Based on his observation, Copernicus proposed 3 distinct motions of Earth. First, Earth rotates on its axis every 24 hours. That daily rotation is what makes the stars appear to rise and set across the sky. Second, Earth orbits the sun once per year. That revolution around the sun explains the changing positions of the planets and the seasons. And third, Earth wobbles slightly, tracing a small circle while it moves through its orbit, a motion we now associate with the tilt of Earth's axis and the phenomenon of precession. These ideas weren't just guesses. Copernicus spent decades developing complex geometric models and astronomical tables. He used trigonometry to calculate the relative distances of the planets from the sun. He ordered the planets based on how fast they appeared to move across the sky. The closer a planet was to the sun, the faster it orbited. That lined up beautifully with what he saw. But even though Copernicus's model made conceptual sense, it didn't improve accuracy. That's because he still assumed planets moved in perfect circles, just like Ptolemy, and that made his predictions only about as good as the old system. In some cases, worse. Then came the telescope. It wasn't invented by a scientist, actually. It started as a Dutch novelty, just a few lenses slapped together by spectacle makers. But when news of this strange device reached Italy, one man saw more than just novelty. Galileo Galilei. He didn't invent the telescope, but he turned it into a scientific instrument. In 1609, Galileo pointed it to the heavens, and what he saw would rattle the old order. First, he looked at the moon. Through the eyepiece, it wasn't the perfect, smooth, divine orb that the ancients had believed. It had craters, mountains, shadows. It looked a lot like Earth. Then he looked at Jupiter, and there, dancing around the planet, were 4 small points of light. Night after night, he tracked them, and they changed position, but always stayed near Jupiter. These were moons. Moons orbiting something other than Earth. This was huge discovery, because the geocentric model claimed that everything had to orbit Earth. But here was Jupiter, stealing that spotlight, with its own system of orbiting bodies. Then he turned to Venus, and that sealed it. Venus went through phases, like the moon. Sometimes it appeared full, sometimes it was just a crescent, and that only made sense if Venus was orbiting the Sun, not Earth. If it circled Earth, you'd only ever see it in one phase. But if it circled the Sun, and we were moving too, then the geometry worked. That little glowing dot proved Copernicus had a point. But Galileo wasn't the one who finally cracked the math. That fell to someone else. someone who didn't even believe in Copernicus at first. Johannes Kepler was a German mathematician and astronomer, deeply religious, deeply curious, and painfully precise. He got his big break when he became assistant to Tycho Brahe, the last great naked-eye astronomer. Brahe was a Danish nobleman who spent decades collecting the most accurate measurements of planetary motion ever made, all without a telescope. He built giant instruments in his observatory on an island and charted the positions of planets with mind-numbing precision. Now, Brahe didn't buy into the Copernican model. He had his own hybrid theory where planets orbited the Sun, but the Sun orbited Earth. He tried to split the difference, but when he died in 1601, he left all of his data to Kepler, and Kepler dove in. He spent years trying to make the Copernican system match Brahe's data, especially Mars. And Mars was tricky. It doesn't move in a nice, simple circle. It speeds up and slows down, loops across the sky. It just wouldn't behave. For years, Kepler tried to force the data into circular orbits. That's what everyone assumed. Circles were divine, perfect. The heavens had to move in circles. But Mars didn't care about philosophy. So finally, Kepler stopped forcing the math. He let the data speak. And what it said changed everything. Kepler discovered that planets don't move in perfect circles at all. They move in ellipses. That was his first law. All planets move around the Sun in elliptical orbits, with the Sun at one focus of the ellipse. This means that a planet's path isn't a perfect circle, but rather an oval shape. Kepler also noticed something else. Planets don't move at constant speeds. They sweep across space faster when they're closer to the Sun, and slower when they're farther away. That's his second law. A line connecting a planet to the Sun sweeps out equal areas during equal intervals of time. In other words, as a planet moves along its elliptical orbit, the area it sweeps out in, say, a month, is always the same, whether it's near the Sun or far. This explained the strange speeds of planets, especially Mars. And then came the third law, the one that stitched the entire system together, also known as the law of periods. Kepler found that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. In simpler terms, the further a planet is from the Sun, the longer it takes to complete one orbit, and this relationship is predictable. Together, Galileo's telescope and Kepler's equations did something extraordinary. One gave people the vision to see a new universe. The other gave them the math to prove it. Copernicus had started the fire. Galileo fanned the flames. And Kepler built the framework that finally made it hold. After the door opened, it didn't take long before others walked through it and pushed even farther. The next generation moved to the next questions. Why do planets move at all? What force keeps them in orbit? Why don't they fly off into space or fall into the Sun? That's where the famous falling apple came in. Newton gave this invisible force a name: gravity. He realized that the same force that made apples fall from trees also held the Moon in orbit, kept Earth circling the Sun, and ruled the dance of planets. He formulated it into a law: universal gravitation. According to him, every object with mass pulls on every other object, and the bigger the mass, the stronger the pull. The farther apart they are, the weaker the pull. Using Newton's law of universal gravitation, we knew that Earth orbits the Sun at about 107,000 kilometers per hour. That's nearly 30 kilometers per second. Mercury moves even faster, around 47 kilometers per second, because it's closer to the Sun and feels a stronger gravitational pull. Mars, farther out, moves slower. Everything fits together. The closer a planet is to the Sun, the faster it has to move to stay in orbit. Newton's math proved it. He connected the motion of the heavens with the motion here on Earth. For the first time in history, we had one set of laws that applied to everything. And just like that, the great cosmic mystery of planetary motion, why they move, how fast they move, was no longer a mystery. It was gravity. But there was something else, something no one expected. Because as scientists charted the heavens with better tools and sharper math, they noticed another motion, a bigger one, a deeper one. The Sun, the thing we thought was at rest, wasn't. It also moving. But where? After the Copernican revolution, the Sun took the Earth's place as the center of everything. No longer did the cosmos revolve around us. Now it was the Earth that moved, spinning on its axis and orbiting the Sun. This idea felt revolutionary, but once the paradigm shifted, the new model, the heliocentric one, began to settle. The Sun, once seen as just another object in the sky, became our still point, the anchor of the universe. Solid, motionless. And for a few hundred years, that idea held. But that would change, not with a physicist, not with a philosopher, but with a musician. William Herschel was born in Germany and moved to England as a composer. But he had an obsession: telescopes. He started building them in his spare time, grinding mirrors and designing optics better than almost anything else of his time. And when he pointed those telescopes toward the heavens, he didn't just look, he counted. Herschel became obsessed with structure. If the sky was filled with stars, were they scattered at random, or was there a pattern? He decided to find out the hard way. He and his sister Caroline began a massive survey. He would count stars in narrow slices of the sky, just a few degrees wide, and note how many he could see in each direction. Over time, these counts painted a picture. He noticed something strange. Some directions had far more stars than others, and the highest density, it lined up with that faint band we call the Milky Way. So he made a map. Based on his star counts, he constructed what he thought was the shape of the universe, and it looked like a flat, stretched-out disk, like a grinding wheel, with the Sun roughly near the center. Today, we know he got the size wrong. He didn't account for interstellar dust, which blocked many distant stars from view. But for the late 1700s, this was extraordinary. He had figured out that the stars weren't infinite. They were part of a structure, a system, and we were inside it. He called it the galactic system. But Herschel didn't know it was a galaxy in the modern sense. He thought this system was the entire universe. He didn't realize that those fuzzy patches of light, those so-called nebulae, were actually other galaxies unimaginably far away. Still, what he did see was revolutionary. He showed that we weren't at the center of everything, not even close. And that flat shape? It meant something. It suggested structure, motion, orientation. If the Milky Way had a shape, then we had a location. If we had a location, then maybe we were also in motion. That's when people started asking a deeper question. Where are we really? And how can you tell what's moving and what's not? Because if everything is moving, how do you know when something is still? That's when we hit a wall. Not a wall of data, but a wall of perspective. Because everything we see from here, from Earth. Our eyes, our telescopes, our instruments, they're all sitting on this spinning rock that's itself orbiting the sun, which, as Herschel suspected, might be moving too. So how can you tell what's really moving and what's not? That's where a frame of reference comes in. Let's try a simple thought experiment. Imagine you're sitting in a train. You're sipping your coffee, reading a book. Out the window, you see another train next to yours. For a moment, it looks like that train is sliding backward. But then, wait. Are you moving? Or is it moving? Or are you both moving? Here's the thing. Without seeing the ground, you can't know for sure. That's the trap of your frame of reference. From inside the train, everything feels still. The coffee stays in the cup. The book rests calmly on your lap. But to someone standing on the platform, you're flying by at 80 kilometers an hour. So who's right? Well, actually, both are. Because motion isn't absolute, it's relative. And when your only window to the cosmos is from inside that moving train, on a spinning Earth, orbiting a star that's moving too, untangling what's really in motion becomes a puzzle. A puzzle that one man, quietly and patiently, set out to solve. Jacobus Kapteyn never saw himself as a revolutionary. He was quiet, careful, a man who loved numbers more than noise. But what he did with those numbers changed our understanding of the universe. Kapteyn was born in the Netherlands in the mid-19th century. By then, Herschel's star maps were already over a century old. The idea that we were inside a star system, what we now call the Milky Way, was accepted. But the structure, the motion, that was still a blur. Telescopes were better, but astronomers didn't just need better tools, they needed a new approach. That's what Kapteyn brought. He started collecting data, not just light, not just position, but proper motion, how stars shift across the sky over time. These were tiny changes, often fractions of an arc-second per year, but with the right math and enough time, they told a story. He gathered observations from observatories all over the world. The Cape in South Africa, Cordoba in Argentina, Sydney in Australia. Bit by bit, he compiled star catalogues, thousands of them. Measured their brightness, measured their position, watched them drift. And then something strange showed up. The stars weren't just drifting randomly, they moved in patterns. Two general streams, like cosmic currents, seemed to flow across the sky. At first, it looked like the stars were grouped into two large rotating swarms. But Kapteyn thought harder. What if this wasn't about the stars at all? What if we were the ones moving? Back to the train analogy. Imagine you're in the middle of a crowd, walking steadily through a busy plaza. People seem to be flowing past you in different directions. But maybe it is the one in motion, and everything else only appears to drift because of your frame of reference. Kapteyn then made the leap. He ran the calculations, and it all fit. The pattern of star motion only made sense if the sun was moving and dragging us along with it. This motion came to be known as the solar apex. According to Kapteyn's results, the sun was headed toward a point in the constellation Hercules at about 20 kilometers per second. Not a blazing sprint, but a steady, silent drift through space. And with that, the sun lost its stillness. But Kapteyn didn't stop there. He wanted to go bigger. If we're moving through the stars, then what is this collection of stars? What is the shape of the system we're inside? Using the motion and brightness of stars, Kapteyn began constructing what he believed was the true shape of our star system. He assumed stars were distributed evenly in space and that their brightness faded with distance. Based on that, he came up with a model. It looked like a flattened, disc-like structure, about 40,000 light-years in size. And in this structure, the Kapteyn universe, the sun sat near the center. It was our first real attempt to map the Milky Way as a whole. Of course, we now know Kapteyn's universe was too small. He didn't know about interstellar dust, microscopic particles floating between stars that absorb and scatter light, especially in the direction of the galactic plane. This dimmed faraway stars and made them look closer than they really were, so his model underestimated both the size and shape of the galaxy. But for its time, it was groundbreaking. Then came a turning point. Astronomers began to wonder about those faint, blurry spots in the sky, the so-called spiral nebulae. Some believed they were part of our Milky Way, but others suspected something more dramatic, that these might be entire star systems of their own. That's where Edwin Hubble enters the picture. Using the Hooker telescope on Mount Wilson, then the most powerful telescope on Earth, Hubble focused on one of the most prominent of those nebulae, Andromeda. In 1923, he spotted something crucial inside it, a kind of star known as a Cepheid variable. These stars brighten and dim in a predictable pattern, and thanks to Henrietta Swan Leavitt's earlier work, that pattern could be used to calculate how far away the star really was. The answer stunned him. Andromeda wasn't just far, it was way beyond the edge of the Milky Way. So far, in fact, that it couldn't possibly be part of our galaxy. This was a massive shift. For centuries, we thought the Milky Way was the entire universe. But now, it was just one galaxy among many. A single island in a vast cosmic sea. But here's what really matters. By studying these other galaxies, we began to see our own more clearly. You can't look at the Milky Way from the outside. We live inside it. It's like trying to map the shape of a forest from the base of a single tree. But with Andromeda and other galaxies, we finally had something to compare it to. We could look at galaxies from the outside and ask, does our galaxy have a spiral structure like that one? Does it have a central bulge, a flat disk, a halo of stars? Over the next decades, astronomers used this mirror effect, comparing external galaxies to what we could observe from within the Milky Way. They mapped gas clouds, star clusters, and the distribution of various stellar populations. They used radio astronomy to see through the dust that blocked our view in visible light. Gradually, a new picture emerged. One of them is a Dutch astronomer named Jan Oort, who took a closer look at the motion of stars near the Sun. He wasn't just interested in where stars were, but how they moved, and what he found was strange. If the Milky Way was rotating like a solid wheel, every star should be moving at the same angular speed, just like the spokes on a bicycle wheel. But they weren't. Some stars were lagging behind, some were moving faster. It looked more like a whirlpool than a wheel. Oort crunched the numbers and realized the galaxy rotates, but not evenly. It rotates faster near the center, slower at the edges. He worked out the math behind this and came up with two constants that described the way stars moved near our position in the galaxy. These constants, now called the Oort constants, gave the first real description of the Milky Way's differential rotation. From that, he calculated that our Sun is about 30,000 light-years from the galactic center and moving at an astonishing speed, over 200 kilometers per second. That's fast enough to circle the Earth 7 times in a single minute. At that speed, the Sun takes roughly 225 million years to make one full orbit around the center. That's one galactic year. And the Sun isn't alone. Every star you see in the sky is doing the same thing, spinning around the center of the galaxy like bees around a hive. We just don't feel it, because we're all moving together. But if that's the case, what exactly are we orbiting? To answer that, astronomers needed better eyes, ones that could see beyond the visible light. So they turned to radio waves. Specifically, they began mapping out the faint, natural radio signal given off by neutral hydrogen atoms. At a wavelength of 21 centimeters, this signal could pierce through the thick clouds of dust that made optical observations nearly impossible. By tracking this signal, astronomers began to map the spiral arms of the Milky Way from the inside. It was like trying to draw a picture of a forest while standing inside the woods. But now, they had the tools to do it. And then came one of the biggest leaps forward, the Very Long Baseline Array, or VLBA. The VLBA isn't a single telescope. It's a system of 10 radio antennas spread across thousands of kilometers. Imagine placing 2 telescopes on opposite ends of the Earth, say, one in Hawaii and one in the Virgin Islands. Now, imagine syncing them so perfectly they act like one giant dish, the size of the entire continent. That's essentially what the VLBA does. It links 10 radio telescopes scattered across the Western Hemisphere to form one super instrument, capable of resolving incredibly small movements in the sky. And by small, we're talking about shifts so tiny they're measured in micro-arc seconds. That's like spotting a coin on the moon from Earth. They use this system to track cosmic beacons called masers. These aren't lasers you can see with your eyes. They're radio signals naturally emitted by gas clouds around newborn stars. These masers act like lighthouses in space, bright, compact, and perfect for tracking. Because they're locked to specific regions within our galaxy, they help us pinpoint both position and velocity. Over years of observation, astronomers watched these masers inch across the sky. They measured their change in position, that's proper motion, and also how their light shifted toward red or blue. That's radial velocity, whether it's coming toward us or moving away. Combine those and you get a full 3D picture of motion, not just left and right, not just forward and back, but the whole dance of stars across the Milky Way. And what did that dance reveal? It showed the stars orbiting the galactic center, but not in perfect circles. Their motion forms a spiral pattern, twisted and stretched by the pull of gravity and the structure of the galaxy itself. Some arms lead, others trail behind. Clusters wobble. Gas clouds shear under tidal forces. But there was something else too, something strange at the heart of it all. As these mesas and other stars were tracked closer and closer to the galactic center, something became obvious. Their speed increased dramatically. Objects orbiting near the center were whipping around at insane velocities. But here's the kicker. There wasn't enough visible matter there to explain that kind of gravity. There were stars, yes, dust, gas, but not nearly enough to hold things together at those speeds. Something invisible was anchoring the galaxy. And all that motion, all that math, all those precise measurements, they all pointed to the same place. A compact, dense, radio-bright spot near the constellation Sagittarius. That spot is known as Sagittarius A. It doesn't look like much in visible light, just a haze of dust and stars, but in radio wavelengths, it lights up. VLBA observations zeroed in on it. And what they found was a motionless object. Relatively speaking, that everything else was spinning around. Its mass was over 4 million times that of the Sun. Its size is smaller than the orbit of Mercury. The only thing in physics that fits those numbers, that small, that dense, that massive, is a black hole. A supermassive black hole. That's what anchors the Milky Way. It sits quietly in the center, barely flickering, while every star, every planet, every gas cloud in the galaxy swirls around it. And still, we're not standing still. Because the stars aren't just orbiting around the center. The entire galaxy is twisting, warping, wobbling. One of the arms we're riding on, the Orion spur, gently rises and dips above the galactic plane like a surfer riding a wave. But even the Milky Way isn't standing still. Our entire galaxy is in motion, drifting, pulled by unseen forces. A car comes racing toward you, its engines roaring. And just as it passes, it changes pitch. Higher as it comes in, lower as it drives away. That's the Doppler effect. It happens when something that makes waves, like sound, moves toward or away from you. When it's coming closer, the waves bunch up. When it's moving away, they stretch out. Light does the same thing. If a star or galaxy is moving toward us, its light waves get squeezed, shifted slightly toward the blue side of the spectrum. We call that blue shift. If it's moving away, the light gets stretched. It shifts toward red. That's redshift. In the 1910s and 1920s, scientists started using this trick to measure the motion of stars and galaxies. One of them was Edwin Hubble, and what he found was shocking. Most of the galaxies he observed weren't sitting still. They were moving away from us, and the farther away a galaxy was, the faster it was receding. Some were flying away at hundreds of kilometers per second. Others, thousands. Hubble mapped this out, and with each new galaxy, the pattern held up. Farther meant faster. Space itself was expanding, and the galaxies were just along for the ride. It was one of the biggest discoveries in the history of science. It meant the universe had a beginning. It meant everything we see today used to be much closer together. It even laid the groundwork for the Big Bang theory. But not every galaxy is running away. There was one that stood out. A familiar neighbor. Big, spiral-shaped. The Andromeda Galaxy. In 1912, an American astronomer named Vesto Melvin Slipher pointed his telescope at Andromeda and measured its light spectrum. At the time, people were just beginning to understand how redshift and blueshift worked with galaxies. And what Slipher saw went against everything they expected. Instead of being redshifted, like most galaxies, Andromeda's light was blue-shifted, meaning it was heading toward us. But back then, that was all they could really say. Just a direction, not the full picture. Fast forward 100 years. Technology has come a long way. We've got space telescopes, supercomputers, and a whole network of radio dishes spread across the Earth. Astronomers use data from NASA's Hubble Space Telescope, combined with precise measurements from the Gaia mission and the VLBA. By tracking the actual movement of Andromeda over many years, not just the light shift, but its sideways motion too, they pieced together a full 3D map of its trajectory. And what they found confirmed it. Andromeda isn't just drifting near us. It's not going to slingshot by. It's locked in. It's on a direct collision course with the Milky Way, and we're heading toward it too. It's not just that Andromeda is coming for us. We're both racing toward each other across the void of intergalactic space. Right now, Andromeda is moving at about 110 kilometers per second in our direction. That's over 400,000 kilometers per hour. And the Milky Way isn't sitting still either. We're drifting toward Andromeda at nearly 300 kilometers per second when you factor in the motion of our whole local group of galaxies. That means the gap between us is closing fast, at roughly 500 kilometers per second when you add it all up. Still, space is big, really big. Andromeda is about 2.5 million light-years away from us. That's roughly 24 quintillion kilometers, a number so huge it barely feels real. At that rate, even with both galaxies barreling toward each other, the closing speed isn't enough to make it happen anytime soon. So no, not tomorrow, not next year, but in about 4 to 5 billion years, the two largest galaxies will finally meet. Now you might picture this as a galactic car crash, stars smashing into stars, chaos and fire everywhere. But that's not how this works. Galaxies are mostly empty space. The stars inside them are incredibly far apart. On average, the distance between stars in our part of the Milky Way is about 4 to 5 light-years. That's nearly 40 trillion kilometers. Even in the denser core regions, stars are still typically separated by about a light-year or more. To give you a sense of scale, if a star were the size of a ping-pong ball, the next closest star would be several hundred kilometers away. So even during a head-on collision between two galaxies, most stars just drift past one another without ever touching, like ships passing in the night. Still, it's not completely peaceful. A few stars might actually collide, especially in the crowded central regions. And a small number, especially ones on the outskirts, might get flung entirely out of the galaxies, tossed into intergalactic space like cosmic castaways. But the real drama happens through gravity. That invisible force stretches and warps the galaxies. It flings out long tidal tails, streams of stars pulled far from their homes. It rips apart spiral arms. It pulls the cores closer and closer together until the two galaxies finally merge into one larger, messier system. But the full collision doesn't happen all at once. The first encounter is fast, a close pass that starts the chaos. But the merger itself, that's slow. It takes about 1 to 2 billion years to fully settle. It's not a crash, it's a slow, graceful gravitational ballet. And when the dance ends, something new is born. A single, massive, elliptical galaxy. Astronomers already gave it a name, Milkomeda. It won't look like a spiral anymore. It'll be puffier, rounder. A huge glowing ball of stars, gas, and dust. Our Sun, assuming it survives, will likely find itself in a new orbit. Not where it is today. Not in a neat spiral arm. It could drift farther from the center in a path more elliptical and erratic than it is now. But the collision with Andromeda isn't the whole story. It's not the only trajectory our galaxy is on, because the Milky Way, along with Andromeda and hundreds of other galaxies near us, we're all being pulled, not just toward each other, but towards something larger, something stranger. But to understand where we're headed, we have to zoom way out. First, past our solar system, then past the Milky Way, then even past the group of galaxies we belong to. Because galaxies don't float in isolation. They gather, they cluster. They follow gravity, like water flows downhill. Let's start small. Our Milky Way is part of a galactic group, a collection of around 80 or so galaxies called the Local Group. It spans about 10 million light-years across. The Milky Way and Andromeda are the two biggest galaxies in this group, each surrounded by a handful of smaller satellite galaxies, like the Magellanic Clouds or M32 and M110 orbiting Andromeda. But this group is only a tiny pocket of the next step up, a galaxy cluster. Clusters are gravitationally bound collections of multiple galaxy groups. The Local Group is just one small member of the Virgo cluster, a much bigger collection of over 1,000 galaxies. The Virgo cluster sits roughly 65 million light-years away from us and pulls on us with its gravity. And we're not just floating alongside it. Our entire Local Group is moving toward the center of the Virgo cluster at a speed of about 600 kilometers per second. So we've got groups inside clusters. But even clusters aren't the end of the story. Clusters of clusters form superclusters, the largest known structures in the observable universe. These can span hundreds of millions of light-years and contain tens of thousands of galaxies. And ours is called the Laniakea supercluster. That word means immense heaven in Hawaiian, and it fits. Laniakea is colossal, over 500 million light-years across, home to around 100,000 galaxies. It includes the Virgo cluster, the Hydra Centaurus supercluster, the Pavo Indus supercluster, and the Southern supercluster, all interconnected in a web of cosmic flows. So, how do we even know all this? How do scientists figure out where galaxies are going, how fast they're moving, and what they might be heading toward? It all comes down to motion. Over the past few decades, astronomers didn't just look at where galaxies are. They mapped how galaxies move. And to do that, they needed more than just redshifts and blue shifts. They needed peculiar velocity, the actual motion of galaxies relative to the general expansion of the universe. Now, this isn't easy. You can't just take a snapshot and know how fast a galaxy is going sideways through space. You have to combine a lot of techniques. One of the most important is the Tully-Fisher relation. That's where astronomers compare a spiral galaxy's brightness with how fast it rotates. If you know how bright a galaxy should be and compare it to how bright it actually looks, you can estimate its distance. And once you know both the galaxy's redshift and its distance, you can figure out if it's moving faster or slower than the general Hubble expansion. That difference? That's its peculiar velocity. Motion caused by local gravitational influences, not just cosmic expansion. That's where the real insights come from. Enter the Cosmic Flows surveys. Cosmic Flows 2, and later the much more detailed Cosmic Flows 3, were massive efforts to gather motion and distance data for thousands of galaxies. Using things like Tully-Fisher, surface brightness fluctuations, and even supernova data, scientists built a 3D velocity map of our cosmic neighborhood, not just where galaxies are in space, but how they're moving. And what they found was shocking. Galaxies weren't just expanding outward, like dots on a balloon. They were also flowing in a specific direction, towards something we couldn't see directly, something big. And the pattern wasn't chaotic, it was coherent, structured. A motion that pointed toward a mysterious zone of space, somewhere past the constellations of Centaurus and Norma, blocked from our view by the Milky Way's thick dust lanes. That's when the real mystery started. What are we being pulled toward, and why? Astronomers had noticed this strange flow back in the 1970s. Galaxies, including ours, weren't just drifting with the expanding universe. They were moving sideways, with purpose, at hundreds of kilometers per second, all heading in the same direction. But when telescopes tried to look that way, they hit a wall, a region in the sky we call the zone of avoidance. It's packed with stars, gas, and dust from our own Milky Way, blocking our view of whatever's behind it. Still, the motion was undeniable. Scientists called the source of this pull the Great Attractor, not because they could see it, but because they could feel its gravitational grip. Entire clusters of galaxies were leaning toward it, and we were caught in that same current. Bit by bit, using X-ray telescopes and infrared surveys, astronomers began to piece together the picture. They found huge concentrations of mass hidden behind the Milky Way's disk, not a single object, but a region of space teeming with galaxy clusters. One of the biggest was the Norma cluster, located about 220 million light-years away. And that cluster, it wasn't alone. It was part of a much larger structure. This region, this attractor, turned out to sit near the edge of something far bigger, the Shapley supercluster, one of the largest known superclusters of galaxies in the local universe. That's what's pulling us. The gravitational influence of the Shapley supercluster is so strong that it bends the paths of galaxies across a wide stretch of the cosmos. Even though we can't see it directly in visible light, its mass is dragging our entire supercluster toward it. We're moving at about 600 kilometers per second in its direction. Now here's where it gets tricky. This isn't a neat, clear-cut destination. We're not falling into the great attractor like a rock into a hole. We're caught in a cosmic tug-of-war. Gravity doesn't just pull, it warps space. So while the great attractor pulls us in, other forces in the universe are also shaping our path. And one of the strangest forces shaping that path isn't a force at all. It's the dipole repeller. Let's slow this down for a second. The dipole repeller isn't an object. It's not a galaxy. It's not even a thing you can see. It's a region of space that's unusually empty. A cosmic void. There's barely any matter there. No major galaxy clusters. No real gravitational pull. But that emptiness, it matters. Because while massive objects pull galaxies toward them, giant voids act like the opposite. They let galaxies drift away more easily. Think of it like this. You're floating in a river. On one side, there's a waterfall pulling you in. That's the great attractor. On the other side, just flat, calm water. No current, no force. That's the dipole repeller. You're not being pushed by it, you're just not being held back. So the waterfall wins. This is what our galaxy is caught in, a kind of gravitational current. And astronomers started to see this more clearly in 2017, when they used Cosmic Flow's 3D data and 3D motion maps of over 18,000 galaxies. What they saw wasn't just a pull in one direction, it was a dipole pattern. Galaxies like ours were streaming, flowing, away from the repeller and toward great attractor. But even this isn't the end of the cosmic motion. When you zoom out far enough, past the clusters, the superclusters, past the filaments and voids, a new pattern begins to appear. A deeper flow, one that stretches across the entire observable universe. All the great threads of the cosmic web, they're not standing still. They're drifting. Somewhere. So far, we've followed the Earth as it spins and orbits. We've watched the sun drift through the galaxy like a leaf in a current. Then we zoomed out and saw that even the Milky Way itself is moving, part of a vast cosmic flow towards something we can't even see. It's already wild to think we're on a moving rock that's part of a moving system that's inside a moving galaxy. But now, it's time to go even bigger. It's time to ask the final question. Where is everything in the universe going? Not just Earth, not just our galaxy, everything. What's the universe's final destination? To answer that, we have to talk about something strange, something that doesn't glow or shine. Something that acts like it's pulling the strings behind the scenes. Something so weird, it shook science to its core when we discovered it. The story starts, ironically, with the end of the universe, or at least with trying to predict it. In the 1990s, two teams of scientists, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were studying exploding stars called Type 1a supernovae. These explosions are incredibly bright, and they all explode in roughly the same way. That makes them perfect as cosmic mile markers. If you know how bright a supernova should be, and it looks dimmer than expected, you know it's farther away. The goal was to measure the rate at which the universe was slowing down. You heard that right. slowing down, because the assumption at the time was that after the Big Bang, the universe started expanding, and gravity, being attractive, was slowly pulling everything back. But that's not what the data showed. When they measured the supernova, something didn't add up. The galaxies weren't just far away, they were too far. The light was more red-shifted than it should be, which meant the galaxies weren't just moving away, they were accelerating. The universe wasn't slowing down, it was speeding up. Now imagine being a physicist and suddenly realizing that every assumption about the future of the universe is wrong. That's what happened in 1998, and instead of brushing it off, the teams double-checked everything. But the results kept saying the same thing. Something invisible, something powerful, is pushing the universe apart faster and faster. They called it dark energy. We don't know what dark energy is made of. We don't even know if it's a thing at all, but we do know it's real, and it dominates the universe. About 70% of everything out there, of all the energy and matter that exists, is dark energy. To understand how weird that is, think about this. Everything you've ever seen, touched, tasted, or heard in your entire life, all the stars, all the planets, every atom makes up less than 5% of the universe. Another 25% is dark matter, which holds galaxies together with its gravity. And then the rest, the biggest slice of the cosmic pie, is this silent force pushing the universe apart. So what could it be? Here's where it gets tricky. Physicists have a few guesses. The most straightforward idea is that dark energy is just the vacuum energy of space. That even when space looks empty, it's not really empty. It's filled with quantum fluctuations, tiny, random blips of energy popping in and out of existence. Now here's the interesting part. When you do the math, quantum theory actually predicts that empty space should have energy. That's not the crazy part. The crazy part is how much. The prediction is that the vacuum energy should be 10 to the power of 120 times stronger than what we actually observe. In other words, quantum theory overshoots the real value of dark energy by a factor so huge it's the biggest mismatch between theory and observation in the history of physics. This is like trying to measure the weight of a feather, and your calculator says it weighs more than the entire Earth. Yes, something's off. And here's the problem. This vacuum energy, the energy of empty space, isn't just sitting there quietly. According to Einstein's equations, energy and pressure shape the fabric of space-time, which means if space does have energy, then it affects how the universe expands. That's where dark energy comes in. We've observed that the universe is expanding faster and faster, so whatever is causing that acceleration has to be baked into the structure of space itself. And that's what led scientists to think, maybe the vacuum energy is the thing driving this expansion. Maybe dark energy is just the energy of empty space. But if that's true, then quantum theory's prediction should match what we observe. And it absolutely doesn't. It's not just a little off, it's catastrophically off. So either something's wrong with our theory, or we're missing a huge piece of the puzzle. Now let's try to picture this. Imagine space as a giant loaf of raisin bread. Galaxies are like raisins baked into the dough. As the bread bakes, it expands, and the raisins move away from each other. That's the universe expanding. But now imagine that halfway through baking, something turns up the heat, way up. The dough doesn't just rise, it starts inflating faster and faster. That extra push, that's dark energy. And the bigger the bread gets, the faster it expands, because dark energy isn't just sprinkled into space, it is space. The more space there is, the more dark energy there is. It's not diluted. It doesn't run out. That's what makes it so scary. So now, we're standing here, looking at a universe that's expanding faster and faster, and the engine behind that runaway growth? Dark energy. This invisible, untouchable force that doesn't clump, doesn't slow down, and somehow gets stronger the more space there is. That's already weird. But now comes the truly unsettling part. Where does this take us? Let's say dark energy keeps doing what it's doing, keeps pushing, keeps stretching space. What happens in the long run? This leads us to one of the most terrifying predictions in all of cosmology. It's called the Big Rip. Here's how it works. In our current universe, gravity is still strong enough to hold things together. Galaxies don't get torn apart. Stars still orbit their centers. Planets cling to their suns. Even though space is expanding, the forces inside galaxies are still stronger than the pull of expansion in their neighborhood. But dark energy doesn't play by those rules. It grows. It's relentless. And in some models, it doesn't just keep accelerating the universe, it speeds up the acceleration. Like, imagine you're in a car going faster and faster down a hill, and then the hill steepens. That's the Big Rip scenario. At first, it's nothing you'd notice. Galaxy clusters would drift apart slowly. The space between the Milky Way and Andromeda would grow too fast for them to ever collide. But it wouldn't stop there. Eventually, the galaxies themselves would begin to stretch. Not just pulled apart, but ripped apart from the inside. Gravity would weaken. The bonds holding stars in place would falter. Then star systems, like our solar system, would come undone. Planets flung out of orbit, moons lost to the void. The tides that held everything in balance, gone. And it keeps going. As the acceleration intensifies, even the Earth itself wouldn't be safe. The force of expansion would grow so strong, it would overwhelm the electromagnetic forces that hold molecules together. The crust would crack, the atoms would break apart. Even protons, the building blocks of matter, could be torn, as space itself stretches beyond what any particle can survive. In the final moments before the Big Rip, the universe would become a storm of disassembled pieces. 22 billion years from now, there will be no galaxies, no stars, no atoms, just pure, unbound energy flickering in a sea of nothing. That time is just a guess, based on one model. It could be sooner, could be never. Because it all depends on how dark energy behaves, and that we still don't fully understand. But not every theory ends in shredding. Some go the other way. There's another idea, and it starts with a question. What if the expansion of the universe doesn't go on forever? What if, at some point, gravity fights back? You see, early in the universe, everything was hot and dense. Space was expanding, but gravity was pulling back, trying to slow everything down. That tug of war has been going on since the beginning, and for a long time, scientists thought gravity might eventually win. This is the theory of the Big Crunch. In this version of the story, expansion is temporary. One day, dark energy might weaken, or maybe it was never permanent to begin with. And if that happens, gravity could take control again. Slowly at first, it would start to pull everything back together. The galaxies that once drifted apart would begin to close in. Structures would reverse. The great cosmic web would contract. Over billions of years, the universe would shrink. Temperatures would rise as everything gets squeezed into a tighter and tighter volume. The night sky would grow brighter, not from new light being born, but from old stars smashing together in a shrinking cosmos. The fabric of space-time would bend inward, like a closing fist. In the final seconds, the entire universe would become a single, hot, dense point. And then, maybe it ends. Or maybe it starts again. There's a poetic symmetry to the Big Crunch, the idea that the universe ends where it began. That the Big Bang was just one act in a cosmic cycle of expansion and collapse. Bang, then crunch. Forever and ever. But there's a problem with this picture. The math doesn't quite line up. Everything we've observed so far, galactic redshifts, the cosmic microwave background, tells us the universe isn't slowing down. It's speeding up. That means gravity isn't winning, at least not yet. So unless dark energy changes dramatically in the future, the Big Crunch doesn't seem likely. But here's the thing. We don't fully understand what dark energy actually is. Right now, it's a placeholder term for something we can measure, but not explain. We know it's causing the universe to expand faster and faster, but we don't know why. If someone ever figures out the true nature of dark energy, it won't just be a breakthrough, it'll be Nobel Prize material. But until then, we're left with what we can see. Still, there's one more possibility, one more future. It's not as dramatic as a rip or a crunch. It doesn't explode or collapse. It just keeps going. And that might be the most haunting ending of all. This is the Big Freeze. A universe that doesn't die in violence, but in silence. Here's how it happens. We've already talked about dark energy, how it drives the universe to expand faster and faster. We've also talked about how, unless it changes drastically, that expansion is here to stay. Now imagine the universe continuing this path. Galaxies drifting farther and farther apart, never slowing down. The stars inside them aging, burning through their fuel, one by one. This idea, the cold, endless fade, isn't just poetic. It's backed by some of the best data we have. Andrei Lind, a Russian-American physicist known for his work on inflation theory, has contributed to models that support this kind of ending. According to current cosmological parameters, measured by tools like the Planck satellite and large-scale surveys like the Sloan Digital Sky Survey, the rate of expansion is consistent with a cosmological constant. That means dark energy likely stays the same over time, not increasing, not decreasing, just humming along, gently stretching space. If that holds true, then the Big Freeze isn't just a possibility, it's the most likely fate of our universe. Now let's zoom out and follow this future step by step. We're in the present day. Galaxies are still relatively close together. Stars are being born in places like the Orion Nebula. Planets are orbiting, life is breathing, black holes are eating, and the cosmic web is still glowing with energy. But time passes, a lot of time. Give it 100 billion years. By then, the observable universe, what we can see, will shrink dramatically. Not because the universe itself is getting smaller, but because the space between us and distant galaxies is expanding faster than light can cross it. Those galaxies will slip beyond our cosmic horizon. We won't be able to see them anymore. They'll still exist, but forever out of reach, like ships sailing over the edge of an ocean that never ends. After enough time, even the nearest galaxies will vanish from view. Eventually, the Milky Way and Andromeda, by then long since merged into one giant elliptical galaxy, will become a lonely island floating in a dark, silent sea. Star formation won't last forever. Stars need gas, mainly hydrogen, to be born. But that gas doesn't last. As stars go supernova or shed their layers, they recycle material back into the galaxy. But over time, that recycling slows down. The fuel runs out. Estimates say that in about 1 trillion years, star formation across the universe will stop completely. The stars that are left, they'll burn through their fuel slowly. Red dwarfs, tiny, cool, dim stars, can last for trillions of years. They'll be the last beacons of light in an otherwise dark sky. But even they will eventually burn out. After that, only the remnants will remain. White dwarfs, neutron stars, black holes. Then we enter what's called the degenerate era. This is the time when there are no new stars, no new light. The universe is made of cold, collapsed objects, brown dwarfs, and black holes, still hungry, still devouring. And time just keeps going. Over the next 10 to the power of 40 years, that's a 1 followed by 40 zeros, these stellar remnants will decay. White dwarfs will cool until they become black dwarfs. Neutron stars might remain stable for a long while, but black holes, they have their own clock. According to Stephen Hawking, black holes aren't permanent. They slowly evaporate through something called Hawking radiation, a quantum effect that causes them to lose mass over time. It's incredibly slow. A black hole with the mass of our Sun would take about 10 to the power of 67 years to completely vanish. Let that number sink in. Our entire universe right now is about 13.8 billion years old. That's nothing compared to the scale we're talking about. In the Big Freeze, time stretches far beyond what we can truly imagine. Eventually, every black hole evaporates. One by one, they disappear in tiny flashes of radiation. No more stars, no more planets, no more light. The universe becomes a place of particles, electrons, positrons, maybe some decaying protons, floating alone in a sea of cold, expanding space. Temperature drops toward absolute zero. Not because there's no heat, but because there's nothing left to generate it. No fusion, no gravity pulling things together. Just particles, scattered across an ever-growing void. Even the protons might not last. If proton decay turns out to be real, then all matter itself could fall apart. Some models say that could happen in around 10 to the power of 36 years. So, what's left? Nothing really, just a whisper of radiation, a background glow from a universe that once burned with stars, galaxies, and life. A universe that expanded until everything was too far apart to interact, too cold to change. Even the concept of place becomes meaningless. The laws that gave birth to everything still remain, etched in a frozen, meaningless void. But there's no one left to read them. And that will be the ultimate fate of our universe.